The flexor carpi radialis and extensor carpi radialis are both muscles in the arm. They work across the elbow to wrist region, interacting with the radiocarpal joint. The radiocarpal joint is the location where the radius meets the carpal bones. Its most important functions are wrist flexion, wrist extension, and wrist abduction. You do wrist flexion anytime you play the piano, write something down, or grip an object. You do wrist extension anytime you open a door, the pushing out motion, perform a push-up, or throw a ball. You do wrist abduction anytime you turn a doorknob, use a screwdriver, or hold a baseball bat. When you flick your wrist, the extensor carpi radialis contracts concentrically, which means it shortens the muscle. Then, the flexor carpi radialis contracts eccentrically, which lengthens the muscle and serves to resist movement from extended to neutral position.
The arm can be represented in a model such as this, where the forearm is a large box and the hand is a smaller one. In this example, the arm is orientated such that the thumb is pointing outside of the screen, as it is in this photo. This muscle here is the flexor radialis, and right now it is not being stretched because the hand is in a neutral position. However, if the hand were to move upwards and a distance x away from the forearm, the flexor radialis would be stretched. In order for the hand to move back to its neutral position, the flexor radialis would exert a force of F upon the hand, pulling it back towards the wrist. The flexor radialis can be modeled as a spring, and therefore the force of the muscle can be set equal to negative kx. To find the length x between the hand and the wrist, we can set it in terms of theta and use trigonometry to solve for x. By setting the width of the wrist equal to a length r, we see that the length x is equal to 2r sine theta over 2. Plugging that back into our equation for the force of the muscle, we find the force of the flexor radialis is equal to negative k 2r sine theta over 2. We know that torque is equal to force times radius, and therefore we can set the torque of our hand equal to the force of the flexor radialis times r. Given these two equations, we can determine the net work done by the flexor radialis onto the hand by taking the integral from theta 1 to theta 2 of the force of the muscle times r. This turns into the integral of theta 1 to theta 2 of negative 2r sine theta over 2 times r, or the integral of theta 1 to theta 2 of negative k 2r squared sine theta over 2. By solving the integral, we get 4kr squared cosine theta over 2 from theta 1 to theta 2, which is equal to the net work.
Alright, so what I'm going to do is in this first clip, I throw it with more wrist, and you can kind of see that it flies pretty straight, and in the second clip, I throw it with less wrist, and it starts to be a little bit more wobbly due to this math that Liam will talk about in the next part. And in this third clip, the throw goes off, and it's more of a wider angle, so you can see what it looks like when it flies straight when being thrown with more wrist. And for this next part, I'm layering the two videos over each other so you can see the difference between the two throws. The one that is opaque, or the one that has a lower opacity that you can see through, is the one with the weaker wrist, and you can see that it wobbles a lot more in comparison to the one with a stronger flick.
Okay, so now I will be talking about the physics of frisbee stability when a frisbee is thrown. So the stability of a frisbee in its flight is primarily determined by its angular velocity. So you can achieve a higher angular velocity by pulling your wrist farther back as you do the flicking motion to throw a frisbee. It works both with the forehand method and the backhand. So the farther back you bend your wrist, the more angular velocity or spin you'll be able to get. So this effect is beneficial for throwing frisbee because it reduces the susceptibility to like wind and other disturbances that can happen to a frisbee. And it can be explained in a couple of different fundamental principles that I'll go over right now. So the first one is right here. This basically just says that angular momentum, or L, is the product of a rotating object's moment of inertia, which is I, and its angular velocity. So we can see here that if the angular velocity increases as a result of us pulling our hand back further, the angular momentum will also increase, which means that the frisbee can resist like external torques that could mess up the orientation or make it wobble. So yeah, another way we can look at it is right here through precession and gyroscopic stability. So precession is the change in orientation of the like rotational axis of any rotating body. In this case, it will be the frisbee. So we can see omega is inversely proportional to the frisbee's angular momentum. So we're trying to get as low of a rate of precession as possible. So we want higher angular momentum. And that explains why. Let's see. We can also note that greater angular velocity in this equation contributes to increased linear velocity, which means that the faster spinning frisbee will like achieve higher forward velocity, which can enhance its like lift as it's being thrown. So yeah, in conclusion, increasing a frisbee's angular velocity by pulling your wrist farther back when throwing it will result in greater stability and reduced susceptibility to external disturbances like wind.
In part one of his mathematical analysis, Liam Trammell goes under the assumption that the wrist of is a spring, and there's like a distance between my wrist and my palm, x, that when you open your like hand up like this increases. So the force that the flexor radialis can produce is equal to negative kx, since we're treating it like a spring. And that's where our explanations for why pulling your wrist back more increases like the velocity of the disc and like the angular velocity as well. So if we say that force of the muscle is equal to negative kx, then ma, F equals ma, so ma equals negative kx. The x increases, m stays the same, negative k is a constant. That means that a has to increase, decrease, whatever, to stay consistent with it. So when x increases, a also increases. And just by looking at this, we know that the acceleration is the derivative of velocity. So acceleration increasing means the rate of change of velocity is increasing, which means there's a greater velocity. And using v equals wr, or v over r equals w, which is angular velocity, we can see that increasing this will increase the velocity here and then increase the angular velocity, which explains why doing this and increasing that force increases the stability, like in how Liam Culligan explains it. And another way to do it is that we can say 1/2 kx squared, this is using conservation of energy, equals 1/2 mv squared and root kx squared over m equals v. So increasing x will increase v. V equals wr, w equals vr. Increasing x increases w. So increasing the distance you pull it back will also increase the stability, because increasing w will increase the angular momentum, which decreases the rate of precession.